Welcome to the Journey Shake Cam. I'm so excited today because we're starting something new. Gas Laws, Part 1. So you can use your prior knowledge to answer number 1, and number 2 is a little practice on some conversions. So do the best you can, and I'll see you in a moment. Number 1 asks how gases are used in your everyday life. Well, there's so many ways. Where do I begin? Well, when I breathe in oxygen and I breathe out carbon dioxide, those are definitely gases, and those would be involved in respiration. And plants use photosynthesis, although they do respiration as well. Photosynthesis produces oxygen from the carbon dioxide. That's how plants use it. Also, when we're driving along and suddenly we go thud, 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 well, that's my tires. Well, I have to have the right amount of pressure in those tires or else I'm having a problem. Also, when I cook using propane or natural gas in some houses, then those would be gases as well. Also, when we see the big blimp or the zeppelins up in the sky, they use helium gas as well. And then sometimes we just play with helium balloons. The biggest reason are weather systems. We have high pressure systems and low pressure systems. And low pressure tells me there will be precipitation. And high pressure is going to be nice outside. So there's lots of ways that we use gases in our everyday life. And I'm sure there's some I haven't even thought of that you'll think of. Number 2 is about conversion factors. And we are going to convert 1,300 milliliters, and we are going to convert this to meters cubed. Oh, it's centimeters cubed. And those would be the same as milliliters, so that would have worked as well. However, we know there are 100 centimeters is equal to 1 meter. And when I cube 100, I get 1 million to 1. And therefore, this number is 1.3 times 10 to the 3. And when I'm dividing by an exponential number, I will subtract the exponents. And 3 minus 6 is minus 3. And therefore, this answer is 1.3 times 10 to the minus 3 meters cubed. Now in B, I am changing 67 milliliters to liters. And 1 liter has 1,000 milliliters. And therefore this answer is 0.67 liters. And that's how you do A and B. In 2C, we have meters cubed, and we are changing it to centimeters cubed. So we're going in the reverse direction. Again, there are 100 centimeters is equal to 1 meter. And when I cube 100, I get 1 million centimeters cubed is 1 meter cubed. Now, when I have exponential numbers and I'm multiplying, I will add those numbers. And minus 4 plus 6 is positive 2. You got to think about those numbers. Minus 4 plus 6 is 2. Now, I could write it as 1.98 times 10 to the 2, or I could just write 198 centimeters cubed. Either number would be fine because they are equivalent numbers. And then for D, I am changing 3.13 times 10 to the minus 4th decimeters cubed, and I'm changing it to centimeters cubed, and I'm canceling decimeters cubed. There are 10 centimeters in 1 decimeter. And when I cube 10, I get 1,000. So I have 1 times 10 to the 3 centimeters cubed is equal to 1 decimeter cubed. When I'm multiplying my exponents, I have minus 4 plus 3 is minus 1. And therefore, I have 3.13 times 10 to the minus 1 centimeters cubed, or 0.0313 centimeters cubed. Either number would be fine. So here we go. We need to talk about ideal gases. Normally we treat all gases as though they were ideal. Well, what does that mean? Ideal gases, well, I have one gas particle that's way over here. And I have another gas particle that is way over here. And one is big, 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 and one is little, little, little. And they have no intermolecular forces of attraction. And so we call them ideal. Ideal gases. And we say that they have no volume, no intermolecular forces of attraction. However, they do have mass. They have mass. And so we call that point mass. That's all they have is point mass. Ideal gases have point mass. And therefore, if something has a real gases would have volume, and we would have to take into consideration their intermolecular forces of attraction. And that only happens when we have high pressure and low temperature. And we'll discuss that again later. However, now in our gas laws, we are only considering gases to behave as though they were ideal. Now we also have some information that we need to understand, and it's called STP, standard temperature and pressure. Standard temperature is 0 degrees Celsius. However, we always, without exception, use Kelvin in our gas laws. And therefore, Kelvin is equal to degrees Celsius plus 273. And therefore, 0 degrees Celsius would be 273 Kelvin. And that is considered standard temperature. Now, standard pressures, there are many, many different units of pressure. However, we have some basics that we use. We have seen before 101.3 kPa, and all of these are the pressure at sea level. And kilopascals are units that are used by the Scientific International System. 101.3 kPa is standard pressure. However, we've also seen 1 atmosphere. And another unit that we see on occasion is 760 torr. And 760 millimeters of mercury. And 14.92 pounds per square inch. So there's a lot of various numbers that are used for standard pressure. And we need to know these because we will be needing to make some conversions between one unit of pressure and another. So these are standard pressures and standard temperature. Now, I hope that you have gotten a copy of the Topic 11 Worksheet A that has Boyles Law and Charles' Law on it. And as a special treat today, we're going to do question number 1. So you have an example in question number 1, as well as the example problem that's provided for you on this worksheet. And I'm going to do a Boyles Law problem first. Now, Boyles Law is V1 times P1 equals V2 times P2. V is for volume and P is for pressure. Now, we need to know the mathematical relationship between volume and pressure. Well, volume, if I select a number of 3 times 1 equals 3, I'm having a hard time writing on this board, equals 3, and I double this 3 to a 6, well, what's going to happen to my other number? Well, when I do the math here, x is equal to 3/6, which is 1/2. So as I doubled one number, the other went down by 1/2. They are inversely proportional. One goes up, the other goes down. They are inversely proportional. Volume and pressure are inversely proportional. And it's important for us to know how they are mathematically related. Now, in this first problem for Boyle's Law, what I do is I write down what are the variables given to me in the problem. Well, I'm given an initial value for volume. Volume is equal to 125 centimeters cubed. My initial pressure is 110 kPa. And if you're at a particular place, that's where you're starting. And when you go to somewhere, that's where you're ending. And so my V2 is my unknown, and my P2 is standard pressure. Now, because I am in kPa, I want to use my standard pressure value for kPa, which will be 101.3 kPa. Now, it is very important that you rearrange your equation for your unknown. Therefore, V2, in order to undo multiplication, I'm going to divide. And once I've rewritten it, solving for my variable, I just put in the numbers. Therefore, V2 is 125 centimeters cubed times 110 kPa divided by 101.3 kPa. And when I do the math, I get 135.7354. And my final answer, I have to look back to my original problem and find the number with the least number of significant digits. And that would be 2. Therefore, my 5 rounds the 3 up, and my final answer is 140 milliliters, or centimeters cubed. Because they're the same value. 1 milliliter is 1 centimeter cubed. And that would be my answer for this problem on Boyle's Law. Finally, let's take a look at Charles's Law. Charles' Law states that V1 over T1 is equal to V2 over T2. V is for volume and T is for temperature. Now remember, we always must have our temperatures in Kelvin. And when I look at these numbers, let's look at the mathematical relationship. Well, if I have 3 over 1 equals 3, and I double the 3 to a 6, what happens to the bottom number? Well, 3x equals 6, and therefore x is equal to 2. As I doubled my top number, the bottom number doubled as well. So they are called directly proportional. They are directly proportional. As one goes up, the other goes up. They are directly proportional. So let's do problem number 1 on worksheet A. Well, my Charles' Law is written here. Now, my V1 given in the problem is 1,150 centimeters cubed. And my T1 is 25 degrees Celsius plus 273, because I always must be in Kelvin. And therefore my T1 is equal to 298 Kelvin. My V2 is my unknown, and my T2 is 100 degrees Celsius, and I must change that to Kelvin, and therefore that is 373 Kelvin. Now again, it's very important that we rearrange our original equation for our unknown. Therefore, V2 is equal to V1 times T2 divided by T1. And then I put in the numbers. And 373 Kelvin is my T2, and my T1 is 298 Kelvin. And when I do the math on this, remember you must put equals in between, and then say divided by, and I get 1439.4295. Then I go back to my original problem and see how many significant digits must be my answer. And the answer is 2. And therefore, I have 1,400 centimeters cubed, because the 3 does not round the 4 up. And that's how you do Charles's Law problems. Now, I know that you can do these problems, and you will do them to the best of your ability, I'm sure. And I can't wait to see you tomorrow. Bye.